Welcome to Ultimate Megaprojects.
Hello, I'm Jack Hyber. Today, I'm diving into a story that sounds almost impossible. $20 billion. Yeah, you heard that right. That's more than the entire GDP of some countries.
But instead, China took that staggering sum and built something that shouldn't exist. A bridge that stretches for 55 kilometers, that's 34 miles, across one of the deadliest bodies of water on the planet. A bridge that engineers said was impossible. A bridge that required workers to dive deeper than the Titanic wreck sits to place tunnel segments the size of office buildings with precision measured in centimeters in zero visibility muddy water while battling typhoons, earthquakes, and currents that could snap steel cables like dental floss. This is the story of how humanity bent the laws of physics and nature itself to connect three cities across the sea. Today, we're diving deep into the Hong Kong-Zhuhai-Macau Bridge, the engineering marvel that changed everything we thought was possible. Intro sequence, Ultimate Megaprojects. Section 1, The Impossible Dream, 045 to 230. Cut to historic maps and archival footage of Hong Kong, Zhuhai, and Macau. Narrator. Before 2018, traveling between Hong Kong, Zhuhai, and Macau was a 3-hour nightmare. You'd either drive around the bay, a grueling 120-kilometer loop, or take a ferry across unpredictable waters. For three interconnected regions with a combined population of over 8 million people and a regional GDP exceeding $100 billion, this was a crippling bottleneck. Cut to animated map showing the three cities and the proposed bridge route. In the 1990s, visionary planners proposed something radical, a 55-kilometer bridge that would leap directly across the Pearl River Delta, slicing that 3-hour journey down to just 30 minutes. But the moment engineers studied the route, they realized this was a nightmare. Dramatic pause. Cut to 3D visualization of underwater geological cross-section. The seabed itself was nearly unusable. Beneath the surface lay 40 to 50 meters of soft marine mud, the kind of material that can't support a bridge column. It's like trying to build a skyscraper on quicksand. Cut to animated demonstration of soft soil giving way under pressure. The currents were relentless. The Pearl River Delta is fed by massive freshwater flows colliding with the South China Sea. These currents don't flow in one direction. They spiral and twist, creating vortex patterns that would stress any structure to the absolute limit. Cut to satellite animation showing current patterns. The shipping channels were impassable obstacles. This wasn't some empty stretch of water. The route crossed two major international shipping lanes, massive container ships, vessels displacing 200,000 tons pass through here daily. The bridge couldn't obstruct them. It couldn't slow them down. It had to be invisible to maritime traffic. Cut to real footage of cargo ships navigating through narrow passages. Aviation created an impossible paradox. Hong Kong International Airport is literally miles away. The bridge towers had to clear aircraft, but they also had to be tall enough to allow ships to pass underneath, an architectural contradiction that seemed geometrically impossible. Cut to diagram of conflicting height requirements. And typhoons were relentless killers. The region experiences Category 4 and 5 typhoons with wind speeds exceeding 200 kilometers per hour. Any structure here would face sustained forces that could reduce most buildings to rubble. Cut to historical footage of typhoon damage. So in the late 1990s, international engineers declared it. This project is unrealistic. The costs would be astronomical. The risks are insurmountable. Everyone gave up. Dramatic pause. Cut to modern footage of the completed bridge gleaming in sunlight, except China, and in 2009 they started building. Instead of trying to solve every problem with a single solution, engineers created a hybrid system, a combination of 4 completely different bridge and tunnel types, all working together as one unified structure. The project required multiple distinct solutions working in harmony. Each section of the route presented unique challenges requiring completely different approaches.
Before anything rises above the water, The real work happens below. Engineers drive massive reinforced concrete piles deep into the soft seabed. They go until they hit bedrock to support the enormous weight above.
First, a steel casing, essentially a giant metal tube, was lowered to the seabed and secured in position with pinpoint accuracy. Then, a massive drill bit spiraled downward, grinding through soil layer after layer, penetrating that weak mud until it reached competent rock. This wasn't simple digging. The drill had to operate in a dynamic marine environment with currents trying to push it sideways. Engineers used real-time GPS and sonar to keep everything aligned. A deviation of just a few centimeters would mean starting over, losing days of work and thousands of dollars. Once the drill reached the proper depth, sometimes over 100 meters down, a steel reinforcement cage was carefully lowered into the borehole. The concrete had to be poured from the bottom up, using a special tremie pipe, a tube that keeps the concrete from mixing with seawater. If salt water contaminated the concrete, it would eventually fail. The entire process had to be continuous, without interruption. Workers operated in shifts, pouring millions of tons of concrete around the clock. After completion, every single pile underwent rigorous inspection. They were tested with ultrasonic waves to check for internal flaws. Load testing was performed. Only when engineers were 100% certain did they proceed. The Hong Kong-Zhuhai-Macau Bridge required over 6,000 of these piles. 6,000 vertical shafts, each one a masterpiece of precision engineering. Once the foundation systems were locked in place, the real structure could begin rising. The bridge deck, the surface that actually carries traffic, is its own engineering marvel. Construction began by installing temporary support systems around each pier, essentially massive steel scaffolding that would hold the first deck sections in place until they were strong enough to support themselves. Initial segments were cast in place. Concrete was mixed on site and poured into steel formwork, then allowed to cure. This process took weeks. These initial sections established the exact elevation and alignment that everything else would follow. For the long spans, engineers used prefabricated deck segments. These segments, some weighing 1,000 tons or more, were manufactured with extreme precision in off-site casting yards. Each one was designed to connect to the next with tolerances measured in millimeters. When a segment reached its position, hydraulic jacks made fine adjustments. Surveyors checked alignment. Only when everything was perfect did workers weld or bolt the connection. Then, the next segment was lifted into place. This process continued, leapfrogging outward from each pier, creating a continuous structure that gradually spanned the entire breadth of the Pearl River Delta. The bridge required 3 massive cable-stayed bridge towers: the Qingdao Channel Bridge, the Zhuhai Channel Bridge, and the Zhuzhou Channel Bridge, each one needing to span 1 kilometer or more with clearance from massive container ships to pass underneath. But the aviation problem created an impossible contradiction. Make the towers tall enough for ships, but not so tall that planes can't fly over. The solution was absolutely ingenious and completely unconventional. Instead of building the towers vertically from the ground up, engineers assembled them horizontally near the water surface. Massive tower segments were welded together, laid flat like a fallen skyscraper. Then, in a series of carefully orchestrated movements, cable systems lifted the entire structure upright. Imagine watching a 300-meter-tall building stand itself up. That's what happened here. Except this building was a bridge tower supporting thousands of tons of cables and roadway above it. The lifting process took days. It had to be agonizingly slow. One cable slightly more taut than another, and the entire structure would twist. Too much speed, and the tower would oscillate, vibrate, potentially causing catastrophic failure. Engineers used real-time strain gauges, sensors measuring stress distribution at hundreds of points, to ensure balanced loading. If any single gauge registered unexpected stress, the lifting stopped immediately. Once upright, the stay cables began installation. These aren't simple ropes. Each stay cable is a bundle of steel strands, sometimes containing hundreds of individual steel wires, twisted together and enclosed in a protective sheath. The cables radiate from the tower like spokes on a wheel, supporting the deck below. An animated diagram shows how the cable forces were distributed. The cables had to be tensioned with precise force calculations. Too loose and the structure would sag, too tight and the tower would bend. Engineers needed to achieve a perfect balance where every cable carried exactly the right amount of load. This was done using hydraulic tensioners, giant machines that pulled each cable with measured force while digital readouts confirmed the exact tension. Cables were tensioned in symmetrical pairs, one on the left, one on the right, to prevent asymmetrical loading. The final result, 3 magnificent towers, each surrounded by a web of steel cables, creating structures of stunning beauty and technical perfection. But the job still wasn't done.
There's a section of the route where the conflicting requirements, shipping clearance and aviation clearance, made a bridge impossible. And there was no natural land to work with. So engineers made a decision. We'll create an island. Not a small island, an island the size of several city blocks, with artificial terrain capable of supporting a major construction site, in the middle of the ocean. The seabed here was absolutely nightmarish, 40 to 50 meters of soft marine mud. Traditional excavation would have created a massive crater as the mud simply slid away. The project would be consumed by the environment. The solution was radical: hollow steel cylinders. Engineers sourced hundreds of massive steel cylinders, some over 30 meters in diameter. These weren't simple pipes, they were huge cylindrical structures fabricated at facilities hundreds of kilometers away, loaded onto specially designed transport vessels and towed to the site. Each cylinder was lowered with extreme precision using advanced positioning systems. Once in position, locked into place with lateral positioning tolerances of just 50 centimeters, the interior was filled with material: sand, gravel, rock, and concrete. What emerged? An artificial island with solid ground where only muddy water existed before. 2 islands totaling an area of over 12 hectares. These islands served a critical function: transition points between the bridge system and the underwater tunnel section. They transformed the impossible into the achievable, and they enabled the most complex part of the entire project. Maintain navigation clearance for massive ships, maintain flight clearance for aircraft, minimize disturbance to the marine ecosystem, operate safely for 120 years without failure. A bridge above wouldn't work, it violated the aviation requirement. Excavating a tunnel from above using traditional tunnel boring machines wouldn't work. The geological instability would be catastrophic. So engineers chose the immersed tube tunnel method, essentially the most complex underwater construction technique ever deployed at this scale. The mega dredging operation. First, dredging. Massive suction dredgers, ships carrying equipment that would process thousands of cubic meters of seabed material per day, worked to create a trench along the tunnel route. But this wasn't simple digging. The Pearl River Delta is an estuary with active water circulation. Dredging had to be performed with precise timing relative to tidal patterns to minimize suspended sediment that could damage marine life. The dredging process removed an enormous volume of material, over 5 million cubic meters of seabed. This material was transported and deposited in designated offshore zones away from critical habitats. Once the trench was complete, engineers had created a highway in the seabed, a prepared surface where tunnel segments could be laid with absolute precision. The tunnel segments, fabrication. The tunnel wasn't excavated, it was prefabricated. Imagine a factory the size of several football fields. Inside, a specialized casting formwork system built specifically for this project. Why? Because the required equipment was so specialized, so expensive, so unique that it couldn't be imported. So China built it domestically, using thousands of tons of steel. Each tunnel segment was approximately 180 meters long. That's longer than 2 football fields. Each segment was several dozen meters wide and as tall as a multi-story building. The weight? 40,000 to 50,000 tons. That's approximately the same weight as 10 Boeing 747 aircraft. Given the massive scale, engineers couldn't cast each segment as a single solid unit. Instead, they divided each segment into smaller modules, some weighing 5,000 to 10,000 tons, which were fabricated separately, then welded together with micro-precision in a controlled shipyard environment. Thousands of workers operating around the clock in shifts performed this work. The process was relentless. Segments had to be completed on schedule, where the entire project faced cascading delays. Each segment underwent rigorous quality control. Ultrasonic testing checked welds for flaws. Dimensional surveys confirmed that tolerances remained within centimeters over a 180-meter span. Hydrostatic pressure tests ensured watertight integrity. Only then were segments towed to the offshore installation site.
Each segment had to be lowered into the prepared trench using cable systems and positioning equipment. But the ocean is alive. Currents shifted, tides changed. Water visibility in the estuary was near zero. Murky sediment reduced visibility to just a few meters. Imagine trying to thread a needle while underwater in the dark, while your hands are 100 meters away, controlled by remote cameras and sonar. The alignment tolerance was plus or minus 30 centimeters. Deviate beyond that, and the tunnel segments wouldn't connect properly. The entire installation would have to be aborted. Hundreds of millions of dollars would be wasted. Engineers used real-time GPS, sonar, and laser positioning systems to track the segment's position as it descended. Hydraulic systems made fine adjustments. Specialists watched digital displays showing exact alignment as the segment inched toward the seabed trench. When the segment was positioned, workers, many of them deep-sea divers operating in extremely hazardous conditions, guided connection equipment into place. Mechanical locks engaged. Watertight seals were verified. Then, tugboats towed the next segment into position, and the process repeated. Over months, segment by segment, a 6-kilometer underwater tunnel emerged beneath the seabed, in darkness, in murky water, in a marine environment that consistently tried to destroy human plans. The final moment, when the last 2 segments connected, they met with millimeter precision, despite being installed under absolutely brutal conditions. Watertight seals held. Alignment was perfect. Engineers achieved something that most experts believed impossible. But this story isn't without its shadows. The project faced catastrophic delays. Multiple workers were killed during construction, a sobering reminder that engineering marvels come at a human cost. Typhoons interrupted work for weeks at a time. Equipment failures set back schedules. Cost overruns exceeded estimates by billions. During the immersed tunnel installation, a segment alignment failure required a complete abort operation. The segment had to be retrieved and repositioned. The cost? Tens of millions of dollars. The delay? Weeks of lost work. Environmental concerns were serious. Dredging, despite careful management, did impact marine ecosystems. Fish populations in certain areas declined. Acoustic disturbance from construction affected whale migrations. The environmental cost of this project, though mitigated, remains controversial in maritime biology communities. There were also corruption allegations. Officials were investigated for irregularities in construction contracts. While the project ultimately maintained integrity, it wasn't immune to the political pressures that affect massive government works worldwide. The economics, this bridge represents something more philosophical.
proof that the natural world's limits are negotiable. When engineers were told this is impossible, they didn't retreat, they didn't compromise. They invented new technologies, they developed new methods, they pushed human knowledge forward. The oceans cover 71% of our planet. They separate civilizations, they limit our potential. If humanity can build a bridge across the Pearl River Delta, what prevents us from building bridges across the Strait of Malacca, the English Channel, the Bering Strait?
Every frame in this video has been crafted through a multi-stage documentary production process, from original research and script development to AI cinematic visualization and professional editing. Human creativity guides every step. A digital documentary host and advanced visual tools are used to clearly explain complex megaprojects, engineering, and global infrastructure. This channel is dedicated to original documentary storytelling and follows all YouTube policies regarding AI assisted and synthetic media, ensuring the informative, unique, and monetization